Good afternoon. In the last 100 years, we have learnt a vast amount about space. However, we have only managed manned missions to the moon. This is where we come in. We are the solar sailors from Exeter Mass School. Our task was to get a 1,000 kilogram payload and a 50,000 kilogram payload from Earth to Mars. However, our limitations were we were only able to use conventional rockets to leave Earth. After that, we had to rely solely on solar sails. A solar sail is similar to a conventional sail. However, it is made out of a reflective material which reflects photons or solar winds to give the spaceship momentum.
The way we could use solar sails to propel our spacecraft was using photon pressure, which intercepts sunlight and therefore moves the solar sail through space, or we could use solar wind. I'll talk to you about photon pressure. This works by the sunlight hitting the sail, and the momentum of the photons is imparted to the sail. If the light is reflected, as shown on the diagram, extra momentum is provided. This can be at an angle if the sail is turned, and this is used to steer. So by changing the angle of the sail, we can change the direction the force is in. This is used to aim towards Mars, and playing around with this in the program helped us get towards Mars. The angle we found was the best was about 30 to 35 degrees, and this was because the pressure was high enough and also the direction was suitable.
Our alternative to using photon pressure was to use solar wind to propel our spacecraft. And solar wind mostly consists of high streams of particles which are made out of protons and helium nuclei that are ejected from the sun at speeds of an average of 450 kilometers a second. Similarly to photons, we would be able to angle our sail to intercept these particles, and them hitting the back of the sail would provide a pressure and therefore propel our spacecraft to Mars. However, we did encounter there would be some issues if we chose to use solar wind over photons. One of the major ones would be we'd have to make our sail incredibly strong and therefore relatively thick, which will make it quite heavy because the high-speed particles would quite easily rip straight through the sail. As well as that, our sail would have to be quite thermally resistant to withstand the intense heating that it would receive from the particles. But overall, we were most interested in the differences in force per meter squared that photon pressure would provide versus solar wind. And to start with, when our sail first opened from the distance between the sun to Earth, photons would provide 3 times more force per meter squared than solar wind would provide. And furthermore, as the distance between the spacecraft and the sun increased, the solar wind would spread out, and therefore the density of the solar wind would decrease, resulting in a 66% drop in pressure as our spacecraft approached Mars's orbit. This overall resulted in photons having an average of 10 times more force per meter squared on the sail than solar wind, so we decided to choose photons to power our sail instead of solar wind. But some of you might be asking, why can't we just use both forms of propulsion? And this would be due to very different angling of the sail we'd want to use, and also the materials we'd want to use on our sail would be very different, whether we wanted to maximize our force between photons or solar wind.
So once we decided to use photons instead of solar wind, we had to figure out what kind of properties we wanted our sail to have. We knew it needed to be lightweight because a heavier sail would weigh down the ship and increase the time it took to get to Mars. It also needed to be highly reflective in order to get the most possible momentum out of each of the photons that hit it, and it needs to be very durable because although we won't be angling our sail to intercept the solar winds will still be present and could still cause damage to our sail. So we decided to use aluminized mylar. This is very highly reflective, about 90%, It's very low density, so it's very strong, but won't weigh our sail down too much. And it's quite widely commercially available. For example, it's used in things such as space blankets. But more importantly, this has actually been tested in a solar sail that NASA launched, so we know it's up to the task. If we use this material, the sail would need to be 5.2 square meters per kilogram of our weight, our payload, so we would scale up the size of the sail in order to not drastically change the time it takes to get to Mars with the heavier payload.
With all this planning at hand, we need to properly understand orbits in order to actually get to Mars, or to get anywhere near Mars for that matter. Orbits follow Kepler's 3 laws of planetary motion. The first law being that an orbit is elliptical in shape and has 2 foci, one being the Sun and the other being another point which is calculated onwards. The second law being that a line is drawn from the Sun to the planet, and this line, this segment, sweeps out equal areas in equal intervals of time. The third law being that the square of the orbital period, which is the amount of time it takes for the planet to orbit around the Sun, is proportional to the cube of the semi-major axis, which is half the length of the longest diameter of an ellipse. If we take all this into consideration, along with other equations, such as the inverse square law, where in essence the further away a planet is from the Sun, the slower it'll be traveling. If we take all these into consideration, we'll be able to work out Mars's speed, its velocity, where it'll be along its orbit. This then allows us to work out what will be the optimal time for us to launch from Earth in order to get to Mars in the shortest amount of time possible. The spacecraft will be using a transfer orbit, which is used specifically for interplanetary travel. And we've also managed to actually model all of these orbits to show it and visualize it in a program that we've made.
So, like Seb said, we can calculate where Mars is going to be, where Earth is going to be, and how we can transfer between the two. But to do it accurately over all the periods of time that it would take us to get there would involve a huge number of calculations. So we decided to create a program to do this for us, for which we used Python. We used Pygame, which is an element of Python which allows us to graphically display it. And it calculates the orbit and position of each of the bodies during the time it takes us to get from Earth to Mars. And it also hence calculates the effect of each body's gravity on our spacecraft, depending on where our spacecraft is between Earth, Mars, and the Sun. It also calculates the force of the photons and how much force it would impart on us, and hence how much forward motion we have at each point in time. So here is our program, and you can see the white blob there is our spacecraft moving away from Earth towards Mars on our transfer orbit. This is the Sun here that both the planets are orbiting. You can see it takes us approximately 259 days to get to Mars when we have 5.2 square meters of sail per kilo of payload. So, yeah, but realistically, having such a big sail for our payload, it makes it very difficult for us to practically assemble, like even slightly begin to assemble this spacecraft. Having 260 square kilometers of sail for a spaceship is kind of quite a lot. So it's not really the most practical way of getting to Mars. However, NASA are now developing ways of using lasers on Earth to project onto the sails, which provides many, many more photons, which gives them a much greater forward momentum and means they can have much smaller solar sail size. It's also much more appropriate for much larger distances, so travelling to nearby stars as opposed to Mars, which is a much, much larger distance. But yeah.
Thanks to Sean Matt for setting us the question, and thank you to Will Foreman, our mentor, who helped us throughout. Thank you for listening, and if you have any questions, please feel free to come and ask us at the poster afterwards.